Hey everyone! In this video, we will try to visualize temperatures across the US in 2019. We'll use the weather data function here, which gives various weather data including temperature. Let's play with it for a bit before heading in. We can simply call a city name, say New York City, and call its temperature to get the current temperature. We can also call the non-metric value after, such that we get it in Fahrenheit instead of Celsius. We can also get historical temperature data. Calling a date range, say from January 1st, 2019 to December 31st, 2019, gives us the below time series, which is essentially a specialized list whose x values are date objects. Notice that it has almost 11,000 data points. We can plot this time series using dateless plot. The disjoint in lines shows us some missing values. We can detect those by applying the cases function and searching for the pattern in which the first element can be anything, but the second element has to have a missing head. Applying the length function shows us 338 missing values, which is much smaller than the almost 11,000 data points we have, so we can treat this missing data by missing data method. Applying the time series function on our original time series variable and indicating we want the missing data method option to be set to automatic, we can retrieve a cleaner looking plot as seen here. Obviously, temperature spikes up in the summer. Now, what if I wanted minimum and maximum data? We can simply call the min or max temperature after New York City to get it. I will also indicate that I want this data by day after my date range. Mapping the time series function with the missing data method set as automatic onto my minimum and maximum time series and plotting the data using a dateless plot gives me the following visualization, which shows that New York City certainly has its hectic weather. Now on to answering our question. Before we head in, let's think about our approach. We'll simply use the geocontour plot to visualize temperatures across the US. By generating a bunch of random points and getting their corresponding temperatures each day, we are able to paint an accurate and evolving picture of the US weather. After getting their temperatures, we can generate a visualization for each day and animate it using list animate. Or we can also turn it into a GIF, which I will show you how to do later. First, let's use the random geoposition function to get 500 random geopositions within the US. You can visualize them by plotting a point on each and visualizing the result through geographics. We see a pretty good even distribution. Now let's get the temperatures. Using weather data applied onto our points, we will get the mean temperature in each day in 2019, making sure it's the non-metric value. We can check the length of our data and we see that it is 500. This is the right number, since we started with 500 geopoints. Notice the functional approach that we used in the previous step. Instead of mapping weather data onto each point, we put all of them at the same time into weather data and got our result. This is one big advantage of functional programming in the Wolfram language. Selecting elements who are not free of missing data and taking their length gives us 0, which is a good sign for us. Tallying the data's heads gives us that we have over 182,000 values, which are all quantities. Let's make sure this quantity is the right one. Getting the quantity unit of our flattened data and tallying it gives us the correct unit that we want, degrees Fahrenheit. Now we'll need a list of all the dates in 2019 such that we can pair our temperatures with the corresponding days. To achieve this, I will use the day range function from the beginning to the end of 2019. Inspecting it using a span gives us just what we want, a bunch of consecutive day-date objects. Taking the length confirms that we have 365 days. Now let's pair the temperatures and days up into a time series. Using temporal data, we can do just that. Temporal data will give us a collection of these time series. Here we can group all the temperature data of the 500 geopoints over time as one variable td. This is another advantage of functional programming, as it helps us do operations simultaneously or one by one if needed. Getting the properties of our td variable gives us many, and we can count the number of paths in the data to confirm that this is consistent. We have 500 paths, which is the same as the number of points we had initially. I wanted to visualize a random sample of the data in a histogram. How does the spread look? This will also serve as some sort of sanity check to ensure our data makes sense. Using the with function, which lets me define a local variable to be used only in this expression, I will define d as a random sample of 3 days from my days variable. Using this, I will plot a histogram by transposing the slice data of my td variable with the random dates selected and set my chart labels to those random dates. This way, the histogram recognizes which temperatures belong to which dates. We see a decently varied distribution, which shows us that our data makes sense. We're almost there now. Before we get to making the big expression, let's generate one single image. Using GeoContourPlot, I will visualize my points being associated with their respective temperatures on January 2nd by calling the slice data of my td variable. Notice that by using the slice data of temporal data, we can easily access the data corresponding to all geopositions. What follows is a bunch of options regarding the visual appearance of the visualization. What we get is this following plot, which shows Florida and California as hot areas as expected. Since we want to generate a bunch of these images and string them together in an animation, let's standardize the coloring and bins ahead of time. The bins are basically what range I will put my data in, while the coloring helps us recognize the bin our region is in. As you can see in the previous geo image, these are the bins and the coloring we obtained automatically. For the colors, I will use the color data for the rainbow and evaluate it at 12 different values. I'm using the range function to make a list of values from 0 to 1, varying by 1/11. Mapping my color data onto that list will give me a varying range of colors. For my bins, I will make them range from 0 to 100, going with intervals of 10. This will give me 12 bins to place my data in, corresponding with the number of colors I have. I will then define my color function, cfunc, based on that. This will guide the coloring of my plots. My idea is to place the colors together in a list, and if the temperature belongs to their corresponding bin, place true before that color. If not, then place false before it. To do that, I will first set up this pure function, which evaluates if the temperature I insert x is less than or equal to an element of my bins variable. It will do this for each element in my list bins. I am also joining it with whether x is greater than the last element. I am then going to riffle it with my colors, which basically means inserting a color between each true or false value. This way, when I apply my which function onto it, once it detects a true, it selects the corresponding color. Now on to the legend. This is based on our colors and bins. We will use the swatch legend function, which will show swatches of colors corresponding to their values. Our first argument would be the colors, and the second would be the actual list of ranges of temperatures. Let's think of it like this. The first will be temperatures less than 0, which is indicated by the less than symbol joined with the first element of our bins list. Then, the following temperatures would be from the second element to the third element to the fourth, and so on. How can we do this? Well, we can partition our list into pairs using the partition function, and use a pure function to join the first element, #1, and the second element, #2, with a dash between them. Finally, if the value is greater than 100, we will just use the greater than symbol and join it with our last element in bins. We will make sure to use toString everywhere here that has numbers so that we don't get any errors trying to join numbers and strings. The rest will be mostly stylistic stuff. Okay, the hardest part is already out of the way. For testing, let's see if we can plot 4 distinct dates but still have the same legends and coloring. I will apply the same code here, associating my points to the slice data of my TD variable. But now I will have the date as a pure variable indicated by the green hashtag such that I can map it onto a random sample of 4 days, let's say. I will make sure to use the legends and color function we set up before. And it looks like it worked. We are consistent. Now on to setting up all images. We will essentially execute the same code, but in here we'll use the special parallel map. This will map our function in parallel to all the days in our days variable, which will speed up computation due to the advantages of parallel computing. We will store that data into our list images variable. Now we can apply list animate here and view the animation directly in the notebook. But I wanted to show the cloud capabilities of the Wolfram language. First, I'll show you how to export a GIF based on the list of images to your local directory. We can use the export function and saying that for our default notebook directory, we want a file animation.gif. This will be based on our list images variable. The rest is some stuff you can manipulate based on your liking. In evaluating it, we get a GIF file exported to our computer. We can now export that to the cloud easily using Cloud Export. We can import the file from our computer and apply the cloud export function on it, indicate we want it as a GIF, and set our permissions to public. Clicking on the link gives us the following satisfying visualization. As you can see, the hot waves are coming from the south in the summer, and the cold waves are coming from the north in the winter. I encourage you to play around with the animation capabilities of the Wolfram language. Perhaps you can do your own analysis on your state or country in terms of temperature.